going like that.
Okay.
So, now, if for some reason I've had students in the past who've been their fingers way back, yeah, this is just a way of doing it. The convention doesn't change just because your fingers are different from everyone else's. It's like also the people who can point their thumbs so that it goes much farther back than that. Yeah, that doesn't change the convention just because your thumb is more flexible than others. Most people don't have an issue with that, but occasionally I get a student who, they're doing that. When I look at it, I see a thumb pointing that way, and they see it pointing that way. You do the boo. Now, in that situation over there, when I was opening that, I applied the angular velocity. It started at rest, the angular velocity was down. But since it started at rest and the angular velocity changed from 0 to something downwards, I had to, my velocity changed. Therefore, there was angular acceleration. If there was angular acceleration, there had to have been a torque. And the torque would have to be in the same direction. So, given my door here, we will say for this exercise, I want to close this as simply as possible. So the question is, how do I close it as efficiently as possible?
Efficiently?
Efficiently.
Like as fast as you can close? Like you want to close it very fast?
Yeah.
You slam it as hard as you can.
Well, I think I need more than that. Was that the most efficient? Actually, it was not.
It was not, okay.
You would do it from the crease?
From the, like push here?
Yeah. No, like,
Squeeze it,
Like-
squeeze it.
Oh, squeeze it?
yeah.
Like a book.
This is, let go. Is that the simplest way? So if I took a book here, it might be more satisfying, but I took the book and I wanted to close it. It is, the most efficient way is to do it that way?
It seems like it.
Huh. Let's take it to the door. Again, unfortunately, it doesn't open in this one. So I want to, to open this one, you just let it go and then we'll do it. All right, so to make that open as efficiently as possible, like push right here at the hinge.
Well, the opening, you do it right from the outside, away from the edges. I think if you're like doing it at the hinges, it's not as strong if you were to do it on the outside.
Okay, so pushing on the outside is
When you're opening it,
and closing it?
you do it from the hinge. It makes sense in my head.
I think you'll find, afterwards, go to a door that you can open and close. This one's locked if it closes. Try pushing at the hinge and then I try pushing farther out. See which one feels like it's easier. But we did hit upon one important thing there, is that part of what's going to make it easier to close is to get farther from the hinge,
Yeah.
whether it opens or closes. So, distance from force to axis of rotation.
That's acceleration. Or that's just
Axis of rotation,
separate.
that's the hinges, the case of the door.
Okay, but that's like separate from acceleration.
Yes, oh, yes.
Okay,
Yeah, that just happened to be taking that space.
okay.
All right, so what else is gonna make it easier?
So like, that's the same thing as the wheel. So if you were to spin the wheel towards the center, it's gonna be harder to push than if you were to spin it on the outside. Like towards the axis
All right, so pushing on the outside, so it sounds like you're
of the
supporting
wheel.
that.
Yes.
All right.
I'm trying to use another example besides the door.
Okay. Yes, but let's take the case of the wheel. If I want to spin the wheel, again, If I push on it here close to the
That's really
axis,
harder.
it is harder to do than
Just
if I push
tapping
it
it.
there.
Yeah, okay.
But if it's just a matter of being far away from it, I'm at the farthest point from it, I'm pushing, it doesn't seem to rotate. What's in the, so what else has to be considered? Not just the distance from the axis of rotation, but what else?
The direction.
We are dealing with vectors. Direction of force with respect, should be a dot there, with respect to lever arm, or as I sometimes call it, moment arm. And there's one other aspect that I think is generally obvious. The more force you apply, the easier it is to slam a door. So the actual magnitude of force. So,
Are these laws? Like, what are they labeled? What do we label them as?
I am getting to the
Getting to that.
formula.
Oh, okay.
Just trying to justify it. So if I want angular motion to occur, if I want there to be a change in angular velocity, so if I have something at rest and I want to get it going, I have to apply a torque. Just like if I have a mass sitting here and I want to accelerate it, I have to apply a force. We're dealing with the rotation, so I'm applying a torque, or G2 Kabuka. The formula for torque. This R here, this is the moment arm, or lever. I think Hewitt calls it the lever arm. I tend to call it the moment arm. So whichever one you want to call it. That's the force. And this right here is a cross product. There's two ways of multiplying vectors. One of them is a dot product, which we use to find energy or work. This one is a cross product. With a dot product, you are multiplying the parallel parts. With a cross product, you are multiplying the perpendicular parts. And if you get confused on which one's which, think about the cross. Basically two perpendicular line segments. So if I have a door with a hinge, that's the hinge, or the axis of rotation. If I apply a force here, my lever arm is a vector from the axis of rotation to where the force is applied. That is my lever arm. So I'm most efficient if the force is perpendicular to that. One last thought. The direction of this, because again, the cross product produces a vector. And for the purists, it's actually an axial vector or a pseudo vector. But for what we're concerned with, vector is fine. You stick your hand in the direction of the first vector. So I have R pointing to the right there. I have 360 degrees of flexibility here. I want my fingers here to turn in the direction, the shortest direction to the other vector. Now, the way it's listed right there, not necessarily obvious, but what we're talking about is if R is going this way and F is going up. All I've done is take those two vectors, put them tail to tail. So put my hand in the direction of the first vector, I want these fingers to curl in the closest way to get to the second vector. So that would be this way. My thumb points outwards. So in this case, the torque that's applied is out. Or another way of looking at it, that force would cause this door to rotate around like that, outwards.
So that's how you solve which direction. If it was like a paper question on paper.
Yeah, you can just, which way would that force cause it to rotate?
You follow with the R and see which way
Yeah, so, or.
to go towards the force.
R cross F,
Out.
out. All right, Brian, I want you to get on the other side of the door. Close it close to here, close it close to there. Try to apply the same amount of force.
I know it's gonna be easy on the outside.
You said you know that, but
Well,
is that
I
just
did.
because? So why were you saying to be closing on the outside? If you're just saying it because you know that's the right answer, or if you're saying it because you know that it's easier to push it to the outside, close farther out.
Well, I know people on the outside is easier, yeah.
Okay, yeah, that's what I was going for.
Can you just draw one more example as if, instead of it going out, like it going down or up?
Down?
Or whatever is different?
For a torque or angular velocity, or I guess either.
Either.
All right,
Or
sitting
like
like this, my axis is up and vertical,
Uh-huh.
so my thumb will point up or point down. If I apply a torque like that, so I'm applying a force, I guess, towards you.
Mhm.
The radial vector is a vector from here to here.
Mhm.
The force is that way. So R is this way, my force is that way. The torque
Okay.
is down.
So that one's down.
It's at rest. If I apply a downward torque, I should have a downward acceleration. The angular velocity should make a positive change, so it'll go from 0 to something positive. So if that is rotating around like that, so my angular velocity is down also.
Okay. Will you draw like how it would be written on a equation or a problem? Kind of like how you just did I understood that.
The instructor is holding a wheel at the front of the classroom.
Mhm.
Holding a wheel by its axle.
Okay.
I might have to do a drawing with that one, but basically I can picture it only like that.
Okay.
He applies a friction force facing the classroom,
Okay.
the middle of the classroom.
Mhm.
So it's this situation and not that situation.
Okay.
It applies a friction force to the left side of the wheel. The wheel in the direction of the students. What is the direction of the applied torque?
So that's how it would be asked. What is the direction of the applied torque? Normal.
Yeah, and for example,
Okay.
we usually or I could have said a wheel is spinning from Susie's point of view.
Mhm.
The wheel is spinning in a clockwise direction.
Okay.
What is the direction of the torque? Towards Susie or away from Susie?
In a clockwise
Sure.
direction.
So clockwise for you would be that way.
Mhm.
Yeah. So the direction of the torque would be away from Susie.
Away from Susie. Okay. That makes more sense.
And another way of thinking about that, to since I think your math is a little bit more sophisticated than most in here. In math, 0 degrees, 0 degrees,
Yes.
90 degrees.
Mhm.
So angles are generally defined in a counterclockwise direction. That's a positive.
Oh.
So if you plus counterclockwise to you, typically that's positive. Clockwise, those are
Negative.
negative angles.
Mhm. That makes more sense. Okay.
There are a lot of ways of looking at it,
Yeah.
and all get to this. They should all get to the same answer.